All right. So in this next session, we are going to talk about API security with a focus on what I call confidential clients, but it will become clear as I go, like what exactly are we talking about? The subset of API security. So just a little bit of context. So why secure API? Why is so many people talking about API security these days, right? This is about protecting your APIs from attack, because APIs are a critical component of modern applications and very much a dependency of, in many situations, your application. So when your API goes down, your application also goes down. APIs allow access to data, and breaches happen through APIs. There have been numerous examples of that. And just in general, I would say attackers look at your APIs as a prime target, right? They skip the client-side application. They try to reverse engineer the API if it's not clearly documented in the first place. And they just try to find a vulnerability. So API security has a really, really wide scope. There's a lot of people involved in making an API actually secure, right? So you want to catalog your API. Some people talk about API discovery. You want to have an inventory of your APIs, because a lot of security incidents happen when people don't necessarily have visibility over the existence of an API somewhere in your organization. You want to find and you want to apply policies. That's a huge aspect of it. So think about runtime API policies that you apply to API traffic, right? So things like authentication, controlling access, so access control rules, rate limiting, input sanitization, threat protection, and things like that. Those are all things that runtime API policies can do. So that's part of API security. You want to find and remediate vulnerabilities. OWASP is a great source of information that talks about what are the top vulnerabilities that you should look for in your APIs. You also want to monitor APIs as part of API security scope, right? You want to monitor your APIs from the inside and from the outside. From the inside, you can tell how busy is your API, how healthy it is, and stuff like that. And from the outside, you get the perspective of how, like you want to make sure your API is accessible from different geographies. For example, there's no DNS issues. There's nothing in the way between your clients and your APIs. And analyzing API security, analyzing API traffic is also part of API security. So I would argue that two critical ingredients to successfully securing your APIs are trust frameworks, right? There's no security without that, and integration. They're critical ingredients, not just because you don't have successful API security without it, but also because they are not, those can be really complicated things. So I'll give you a couple an example for each, and before I pass the Skip here. So integration, right? So we are an API gateway solution, and we're definitely in the middle of that. When customers do API security, our gateway needs to integrate typically with an identity management solution, for example, and things like that, right? But even if you look about, if you think about AI or behavior-based API security, right? So, Willy Wonka is selling you this big data solution, does behavior analysis, machine learning, AI. It models your API traffic, crunching the numbers, looking for anomalies. So how is that API security, right? And the way that that's API security, that's important, is that in the API layer, you need to be able to derive data from the API traffic that's relevant for that solution. So that's integration, right? You need to instrument that everywhere in your API. And then on the reverse side, if your AI engine discovers something that's a threat, and then you need to maybe block a specific client or a specific token or something like that, you also need to instrument that into your runtime API, right? So this is how this API security. So integration, there's a lot of different examples of where integration is required to make API security work. And API security relies on trust frameworks. Trust is what allows integrity, right? Make sure that the data that comes to the API is coming from the client that's supposed to. So there's a lot of different trust relationships, right? If you think about the client-side application needs to trust the API. So what is the trust framework for that, right? So through DNS and certificates, in some cases we utilize things like certificate pinning. That allows a client-side application to trust an API. The API itself needs to trust whoever the token issuer is, because very often that's a different party, right? So there's a trust relationship between the runtime API policy enforcement that applies the authentication rules and the token issuer. Again, that's very often based on PKI, like certificates or a shared secret. The IDP, the identity provider, needs to trust the user, right? And that's typically a password. That's how you know that it's your user. Or maybe there's some MFA or some FIDO involved. And now the IDP trusts the user based on that, issues a token, which itself is trusted by the API. So there's a lot of different layers of trust, right? And one that is the one that we're going to focus on in this presentation is how does the API trust the client application itself, right? So people have been using things like API keys to say, this is the application that's calling the API, right? We're not talking about the user here. We're talking about the client application itself. And that's difficult. A lot of people have been struggling with that. I met a lot of customers. It's like, but how do I know for sure? Like, is it a mobile app? Is it on a public app store? How would you expect, right? You can't expect that this is the application that you release because somebody's going to reverse engineer it, get the API key out of it. So you don't really know. And then that has security implications. So I would like to invite my esteemed colleague, Skip, from Approov to deep dive on this topic of client attestation. Over to you, Skip.
Thanks, Francois. I'm not sure I've ever been called esteemed before, but I'll take it. Oops. And I just dropped the mic. Wow, what does that mean? Okay. So my name is Skip Hovsmith. I work at a company called Critical Blue on a product called Approov. And we're focused very much on mobile security and API security together. And I want to talk to you about client attestation and some of the real pieces I think are missing that we can improve on. So the focus when I talk to customers is quite often on, gee, we got to make sure we know who the user is, and we really have to protect the back end. And my focus is on everything in between those things. Establishing trust, as Francois said, in the app itself, in the device it's running on, and in the channel between the app device and the back end. So I'm going to focus primarily on mobile apps. I'll touch on web apps a little bit towards the end of the presentation. Here's what you're working with. You've got a mobile operating system that the good news is there are some roots of trust with hardware-backed kind of operations and secure enclaves and trust spaces that you can leverage to establish some core trust. And there is a decent model of application sandboxing. So one app cannot get into another app's sandbox. And that mostly works. And then the apps themselves, contrasting that with web apps, have the ability to inspect themselves. So they can introspect their code, they can look at what's going on in their environment, and they can participate, therefore, in their own defense. Attackers, though, have quite good advantages. First, they own the device that they're running the application on, so they can do whatever they want to that application and to that device. The application itself is in a Play Store in the public domain. People can go and access it, take a look at it, and start attacking it directly. So it's relatively easy for attackers to get in there and see what's going on and do their best to attack and cripple the application. So API keys are kind of the canonical way that we typically defend APIs by giving a secret to an application, which will then present that to the API to say, here, trust me, I have the API key secret. Unfortunately, the API key itself is kind of like cash. If you have it, It doesn't tell you anything about who you are. I could be a real bad, evil guy who somehow got my hands on an API key, and I can go and use that key just like cash. So these keys, unfortunately, are on mobile devices pretty easy to steal. If you want to find a secret and you're willing to work hard enough, you can usually always extract it. There are plenty of tools that exist in various domains to go ahead and help you do that. Many of these tools serve honorable, good purposes, but they can also be used for malicious ends. So you can find secrets that have been inadvertently checked into GitHub repos, for example. You can take the app code that you got in the public domain and you can reverse engineer it, take a look at it, break through obfuscation and see what kind of hard-coded secrets can you find in the app, API keys being probably the #1 thing that you'll find there. You can exploit the mobile environment to try and hook into areas to try and observe or change behavior of apps in order to get your hands on some of those secrets or user credentials even. Then you can also, even though you are likely protecting your channel with TLS, there are ways to exploit and break that trust model and get in and man in the middle and extract all sorts of stuff and see every API call that's being made. User authorization, the good news about user authorization with OAuth, for example, is that there's a pretty good model that's defined that allows a user to grant access to an application to go ahead and make an API call through, and the back end doesn't know a lot of the PII and credentials, passwords, etc. of the user itself. So good model. But again, like API keys, it really doesn't guarantee too much about the app. When the user goes to sign in, you usually see a screen that says, is it okay to proceed? And if you click that, you're basically saying, yeah, I think this app is pretty good. That's not strong security. And most people just click through right away. Additionally, in the kind of back and forth that's going on, there is a client ID and a client secret, static secret. Looks a lot kind of like an API key ID secret pair. But even in this model, that secret is recognized as being easily stolen. So on a mobile device, we don't even count on that secret being there. And we use some other methods to try and do as good as we can at guaranteeing things. But it's just, you can't, none of these protocols are guaranteeing the behavior of the app itself that's making the request to get authorization to your backend. So in a typical mobile attack, if I was trying to break in and see what I could get in your backend through your API, I control the device. So I would go ahead and start probing everything I could find. I would start with a static app and use some tools to see if I could extract any keys, whatever other kind of secrets you have lying around in your app, and start collecting those. I will try and root or jailbreak your device, so I'll try and get root permissions so I can break that app sandboxing model and walk around and see what else I can find and get access to, still collecting credentials and secrets as I go. And then I will exploit the runtime, adding instrumentation frameworks, for example, like Frida, to allow me to hook into the application that's running, and where you are saying, am I safe? And the function's going to evaluate something and come back with a yes or no. I will hook that call and say, yes, of course you're safe, continue. And so you can manipulate it that way. You can tamper with the app and recompile it and rerun it, and repackage it. So you've got a lot of buttons that you can push to amass the credentials and the secrets and everything you need to go through, understand the API calls. And once you have everything you need, then your next step is to move to an exploitation phase. So here you've got what you need to impersonate an app and start making API calls. So you can either start sucking data out, or you can start manipulating backends. You can try and degrade customer experiences. In, for example, a sales application, you might go in and notice sales are coming up, and you might try and put orders into shopping carts for everything that's popular to try and drive customers off that site for whatever reason. You can also launch very sophisticated DDoS attacks that are launched at the application level. So they're not so easy to stop at the lower levels. because these look like legitimate traffic, legitimate API calls that I'll just make calls that I know are going to use some expensive database operations, just pile them up. So it's really hard to back off on those kind of DDoS attacks. So this is a financial payments app. This is traffic on that app over a 24-hour period. The top are successful uses of that API, legitimate uses. The bottom is failures. Now, it's only a couple percent of the overall traffic in this, which is pretty good. This is a very well-defended app. But the important thing to note down here is 24/7, there is constant probing of this application. Can we get through? Can we see something? Is it worth our time to go further? So the good news is that what you want to do is invest enough that breaking your API is expensive. It doesn't have to be perfect, but if it's more expensive than the other guy, then the attacker will pivot to the other guy. So people say, okay, great, I've got API defenses in my backend. Isn't that good enough? Well, the backend is going to, of course, check the API keys, check that the user is authorized to access your API. But from there, you're sitting in the back at the end of the process looking out, and you don't have all the information that you could have at that point. So some typical things you might try, Francois mentioned rate limiting. So in that case, you're trying to look for too much traffic coming towards your backend. At that point, you'll start to shut it down. There's a typical leaky bucket model that's used. When that bucket fills up and it's not leaking fast enough, then that short circuits some evaluations. Unfortunately, you start killing traffic, you don't know whether that's legitimate traffic that you don't want to kill or illegitimate traffic that you do. There are behavioral type approaches using machine learning, for example, where you train up a model to see, does the pattern of API calls that I'm seeing, those API sequences, do they make sense? Are they normal? So if you train your model well, it will attempt to follow those and do as best you can. It doesn't catch sort of new exploits as they go through that it hasn't been trained on, but it's doing a pretty good job of as long as the training is good. But the bottom line is that at best, these are educated guesses as to what the traffic looks like. So there's going to be some statistical false positives and false negatives that you're going to get. So as a result, both for rate limiting and for these kind of machine learning approaches, often companies choose to run these controls quite loosely because they're scared to death that they will hurt a customer's experience by falsely killing their traffic and not the other. So these are vitally important in the back end. They're good first line defense, but they're problematic because they're not perfect. So App Attestation, I think, fills in some of this space and builds up trust. And as I said, I want to focus on 3 different areas. I want to assure that the API calls that you're going to evaluate in your backend are coming only from an authentic and untampered app, a real app, not a bot, not something impersonating that app. That app is running on a real and a safe device, that environment is not compromised, and that it's communicating over a secure channel so an attacker can't get in the middle of that device. So those are the aims we're going for, and I want to stress this does not replace any other defenses. This is in addition to, this is a defense in depth type approach. One other thing I wanted to mention, you often hear that what we need to do more today is shift left. We really need to focus on doing better testing of our APIs, on removing every vulnerability we can in APIs. Totally agree that we need to do that, but I think that's only half the piece. The operations side, the runtime side, you also need to invest in. So I would claim you need to shift left, yes, but you also need to shield to the right, move over into the operating space. So in an unattested environment, even a perfectly implemented API, if I can get a hold of your API keys or your user credentials, then I can abuse your API, even if you invest 100% of your effort in making that API totally vulnerable free as you implement it. So with an attested environment, I'm going to claim that even if your API is not perfect, even if there are some vulnerabilities internal into it, given that the only way those APIs should be callable, should be accepted by you, is if they're coming from a legitimate app, that means the only kind of API calls you should see are generated from the app itself. If I tamper with the app to try and do something, to hook something else, it will fail. If I do anything trying to exploit that API, it's going to fail. So even if there are some areas of your API, for instance, if you have some BOLA vulnerabilities, where if I can just hook a record with an ID, I can try a different ID and randomly try and see what I can find. Even if your API is not sensitized to block that, a regular app is not going to make that call. So I think it's really important to spend as much time and effort on the operations on the runtime side, establishing trust, as you are also trying to get all those vulnerabilities out of your API. Oops, did I get stuck? There we go. Okay, so a recommended attestation architecture. One, rather than a static secret, I'm going to adopt kind of the OAuth kind of model of using a time-limited, short time-limited token. So I'm going to take the static secret and use that to sign the token, which is then going to be passed with an API call that says, I have established trust and integrity in this solution. So because it's going to be short-lived, I would recommend just a couple minutes. Then you're going to be reattesting your environment and your device frequently. So that means that if somebody were somehow to get in the channel, all they're going to get is a short-lived, excuse me, a short-lived token, which they can exploit for a little bit if they can get their hands on it. Secondly, I'm going to pull that secret and that signing off the device into an external service. This is kind of analogous to how we do OAuth and user authorization. I'm going to create a service that's going to attest the environment that it's observing. It's going to hook into the running app by dropping an SDK into that app, which will give it the directions to enable it to walk through and look at the integrity within the device and the app itself. So now I've moved the secret off device. I get an additional pop for that because now that the secret's off for that, off device, if the secret gets somehow compromised, I can just change it in the service and I'm instantly off and running with a new secret. So real benefit to get that off, as well as all the security decisions I'm now going to be making off device. And it's a lot harder to hook something that's across and in another server somewhere. It's pretty much impossible to do that compared to using instrumentation frameworks to hook things that are going on in between. And so the only thing I'm going to add is analogous to the user authentication token checking is an additional backend check that's now going to check these short-lived tokens as well. So how do we do these sorts of things? Well, before you release an app to an app store or Play Store, you're going to register it with the service. It could be the Play Store itself if the Play Store is doing this type of attestation work, for example. Once it's registered, then the service has a sense of what the sort of DNA is of the application. It knows how to figure out what is an authentic app. So it will, when it will use the SDK, it will first do a check of the app itself to make sure that the app has in no way been tampered, that it has all its pieces and only all its pieces. So it's the real source code running untampered on the device. Then it's going to pivot to the runtime exploits and see what can it detect there. There's a whole range of things it's going after. Is the device rooted on Android, or is it jailbroken on iOS? Are there instrumentation frameworks running that are trying to cut in and do different things? Is this running in the debugger? Is it really an emulator that's running in a farm somewhere trying to pretend that it's an application? So a whole bunch of things, and they evolve daily. The runtime is kind of a cat and mouse game with people trying to continually introduce new exploits into that runtime system. On the channel side, we're not so much checking the integrity as we are trying to boost it and lock it down. So as I mentioned before, TLS is good, but in the mobile space, it's not perfect. Every device, and this would be the same for a web browser as well, has a notion of a trusted store of certificates. And when the app wants to connect to a service over here, it negotiates through TLS to find a certificate that would be presented by the service it's connecting to. and it would walk up a series of intermediate chains until it finds a rooted certificate that it already trusts in its device trust store. Good model, except that the trust store itself can be sort of broken into, and we can add additional trust items into that device global trust store. So if I'm a man-in-the-middle guy and I want to get in between your system, I'm going to take my certificate, I'm going to inject it into your device store. And now when you're saying, hey, I'd like to talk to Joe's backend API service, the man-in-the-middle replies with the certificate and says, that's who I am. We check the device trust store, bingo, we're in. So we're freely decrypting the traffic you worked so hard to encrypt. We can take a look at it and easily re-encrypt it using just vanilla TLS to go through, so we can observe, we can manipulate. It's a great way to reverse engineer APIs and collect credentials. Very, very popular way to attack in the mobile space. How do you beat that? Is with a concept called certificate pinning. So here we take the actual certificate that we're expecting and we put it in sort of an application level trust store that's guarded within the SDK that's very heavily defended inside this application. So now we'll check the device trust store and say, well, okay, looks good so far, but what about the app level? Is there a pinned certificate there and are we matching it? So in this case, the device would say it's okay, but the application would say, no, this is not Joe's service because it didn't present the right certificate pin. One of the challenges with certificate pinning, however, is that certificates expire. And you've probably heard of situations where somebody's big service was down for a couple hours because all of a sudden a certificate pinned and essentially bricked the application. So this is a case where we have an advantage of having this remote attestation service off here. We can actually use that to manage the certificate pins here. So we can regularly rotate pins by sort of injecting them from that attestation channel in. We can observe it if there ever is a problem. You can go in there and generate new certificates and inject them into the system. Rolls out as each device attempts to attest, it's going to get the updated certificate pinning information. So it's a nice advantage of having this in place in that it solves a lot of the maintenance issues, which frankly have stopped quite a few people from actually implementing certificate pinning because they're scared to death they're going to brick their app. So what options do you have if you want to introduce attestation into your flow? Both Google with Android and Apple on iOS offer a flavor of attestation. Historically, they kind of started out checking the device level. Is this device, has it been tampered with, the device itself? And then they evolved towards checking some features of applications as well. So it doesn't cover everything, but it's a decent base. It can sometimes be a little bit slow. So you might not want to do it in a runtime environment. You might want to do some of these things when the app launches, for example. And it's not available in all markets. In Android, for example, if you don't have Google Play services, you don't get this capability. So if you're in a market that doesn't have that, you can't use this. And also, it's being introduced in newer OS versions. So some of these capabilities will not be in the older OS versions. So it's a good thing to look at and to use, but it's not universally useful at this point. You can go to independent packages. Sometimes these are keyed towards your mobile technology that you're using, the platforms that you're using. You can find root and jailbreak, for example, detectors. They're okay, but there's a constant battle going on. So they don't keep pace with what's going on quite often. But they're a good open source way to sort of dip your toe into it, but they certainly are not going to cover everything. I threw in package signature checkers there, so that's kind of a poor man's, has this app been tampered with? Does the signature look right as you go through? So you can start with those if you will. Commercial solutions, mine being one of them, and typically are trying to cover the whole spectrum, so they're broad and we're in the trenches fighting every day to keep evolving the capabilities. They cover not just the device and the app, but also the channel security. And as I said, man-in-the-middle type stuff is major attack vector that we have to defend against. We can optionally throw in safety net and device checks. So if you're in a market or running an OS that uses it, you can do that. And the advantages to this is that we will provide, any commercial solution should provide a uniform API. So using device check on iOS and safety net on Google, very different APIs, very different terminology, very different concepts. You can wrap all that into a uniform SDK, so you only have to do it kind of one time, and you let the vendor figure out how to make it all work. The last option, which I thought I would mention just to say don't do it, is roll your own. I talk to people, especially when they're focused on one particular technology, they believe, yeah, I can do some of this stuff myself, but they don't understand the investment that's required to keep pace with the hackers that are out there going on. As Francois mentioned, API attacks are super big, and with the leverage you have in mobile is a frequent vector that hackers use to try and get into your system and look at the APIs, because there's just a lot you can do within this space. So please don't roll your own. Okay, what did I do? Okay, sorry about that. Okay, so we've got an attestation channel. I already mentioned there's at least one additional thing we can do, which is simplify certificate pinning management. What else could we possibly do with this off remote attester service that's sitting here? I'll just give you a few examples. One is that now you can make security changes on the fly. If this was baked into an application at the endpoint, you wouldn't be able to change security policies. A customer would install the app, it would say, we're gonna block routing, and you're gonna have to make that decision before you go to production. If you've got access to a remote service, you can make those kind of security policies on the fly. Retail vendors, for example, they don't want to at all touch customer experiences. So if a guy on a rooted phone pops in to buy something, you don't want to stop him until you find out that you're losing too much money because guys with rooted phones are somehow getting through and breaking through. So you want to be able to go to market one way and change your policies as you go through. So there should be a fine-grained ability to change those sort of things. You can also do things like, got to use the right terminology, accept listing and deny listing. So you can universally reject certain individual devices that you find objectable. You can add to the accept list any devices that, no matter how bad they look, just give them a token. And that would typically be used in, say, a testing environment where you just want to get this kind of work out of the way so you can focus on your functionality, for example. Another thing you can do is bind the user token you're using to these attestation tokens. So typically, the application token would take a hash of the token for user authorization and add it into the payload before it makes a signature. So at that point, if I have a random user credential and a random access token, before I could use them like cash, now I have to use them together and only together. So it's kind of like when you got on a plane to come here, you had to present your ticket, which had your name on it, and your driver's license or passport to prove who you are. So now they're locked together. So we're making it a little bit harder. You have to find exactly the right pair to go forward. Another thing you can do, I've been sort of assuming that you're in control of your back end. You use a really good proxy in the back end, so your app only talks to your API. In reality, on average, for an app, there's like 40 different APIs being called within an application that we see. That's a stunning number to me. Many of those are third-party apps, so you don't control the back end. The vendor is going to give you a key, and if you want to call that directly from your mobile app, not go through proxied through where you can control the back end, but if you want to call it directly, then there's that API key, statically probably sitting in your code somewhere. What happens when the vendor just decides to change the API key? Do you have to roll out a whole new installation to all your users? So how do you protect that? So you can add the capability within this SDK to essentially allow you to call your API with some placeholder device. And when your networking stack sees that placeholder, it will reach out to the remote service and say, give me that API key. And it will rewrite that as it's walking through the networking stack. So now the API key is always stored off device. It appears momentarily in your runtime to be added to the API that goes through. So we're now calling third-party API keys. We're not sending a token to those third-party services, but instead we're sending it the API key we need. But that API key is not really appearing on your device where it can be exploited. Again, you have the ability to instantly change that API key. So you're, again, getting that benefit of that remote service. And then the last kind of trick you need to do is we talked about certificate pinning, but you can't necessarily pin a third-party API because you don't control that back-end service. But what you could do is kind of go the route of browsers, and you could pin all the standard browser trust routes that are there, which will cover everybody that wants to be reached. And you can put them in your app. So now, yes, they're in your device trust store. They could be compromised there, but they're not going to be compromised in the app protected within the SDK. So it would be great if I could sit here and tell you we can do exactly the same thing for web apps, but we can't, unfortunately, because the mobile operating system is grounded in some trust routes. The browser model, it does not give those same kind of guarantees. The browser model also does not have guarantees that you can inspect the code that is sitting within the browser. We throw JavaScript in and out of that browser all the time. It's very dynamic. It's very easy to get in there. There's not easy debugger detection capabilities. So a lot of the tools that we use on the mobile space are not really there on the web space. So what do you have to do? Well, the principle of kind of local measurement, grabbing everything you can find, still applies. And we see that most commonly in CAPTCHAs, the visible ones where you fill out the puzzle, as well as the invisible ones that are evaluating what they can in the browser. Typically, they're looking to gather whatever kind of contextual information. Is this an IP I recognize as being legit, or is it something that's not in my accept list? You can fingerprint the browser instances, trying to understand individual browsers and gathering some information and knowledge from that. You can often fall back on assessing what the human-computer interactions are going on. So if this is a browser on a cell phone, is it jiggling a little bit? Is the mouse being moved that looks like a human? And all the hackers are trying to emulate in their bots that same kind of motion. So there's, again, another one of those back and forth games that goes on. And you can carefully try and tighten those back-end controls you have in place, but you're usually scared to death of harming a customer's experience. So it's a tough trade-off. So this is a difficult environment to do well. It's probably constantly evolving. Maybe we'll see some work in improving formal attestation within the browser space. I'm not seeing it happen anytime soon. So I hope I've convinced you why you should consider client attestation. It provides this runtime integrity that's missing, including the app, the device, and the channel to your backend API. It's fairly easy to introduce. In addition to the runtime integrity, it also gives you a lot of runtime agility. We talked about switching in and out API keys on the fly without too much difficulty, for example. It inhibits API abuse, even when you don't have a perfect API implementation. So by restricting your API calls to only legitimate apps in a safe environment, you're not going to see some of those widely exploitive type calls getting through. And one thing I didn't really touch on is it's going to help block API reverse engineering. One of the biggest ways is just blocking man in the middle. When I am given the task of trying to understand your API so I can start to figure out how to exploit it, that's where I go first. I just want to get some traces of your API calls, see where the credentials go, see how things are going, throw that in some fuzzing, see what I can do. So if you can't get into that channel in the mobile space, then I can't get access to my favorite tool to go through. So if you can't reverse engineer the API, even if you're not using all these tricks, it's a lot harder for me to try and impersonate legitimate API traffic. So I hope you'll consider adding these kind of tools and filling out this model of everything between the user and the backend and establishing trust in that whole space, and add it to your toolkit. Thanks for your time.
Thank you very much. So thank you guys for joining us this morning. We have another couple of hours this afternoon. We have Dan's going to be talking about API resiliency. We have Gary calling in from the UK to be talking about emerging patterns with gateways. And then Balo's going to finish the day with the emerging strategies around API gateways. So in the meantime, it is lunchtime. So there are 5 different, there might be more, different buffet areas. One right out here, one all the way down, and several downstairs. Feel free to hit the Partner Pavilion. That's where you'll find a lot of your favorite vendors, such as Broadcom Software, if you want to stop by and find out anything more about Broadcom. And with that, we'll see you at 1:40 local time. Thank you.
Hi, everyone. My name is Daniel Godet. I'm actually an API Academy member. Today, we're going to be covering improving API resiliency using API gateways. And sorry, there was a bit of technical difficulty, so we're starting this session again.